That brings us to this idea of trying to approximate the binomial distribution with a normal distribution. So let's have a look at this example. So we're going to estimate the probability that a school of 1,200 students contains more than 150 left-handed students. Well, how on earth would we solve this problem? We could take a sample, we want it to be reasonably large, so let's say 50 students, and physically count the number of left-handed students. From there, we could estimate the probability for the whole school. So let's say our sample contained 8 left-handed students. Then we'd estimate the probability of being left-handed as 8 out of 50, 0.16. Now, using that estimate, it is a binomial situation, because either they are left-handed or they're not left-handed. There's only 2 outcomes here. So if I let x equal the number of left-handed students, I'm saying it's a binomial distribution. We know there's 1,200 in total in the school, and the probability of them being left-handed is 0.16. We want to know the probability that there's more than 150. Well, I'm going to use the complementary event, but even then, that's a lot of calculations to do. So I've got to work out the probability of none of them are left-handed, 1 of them, 2 of them, 3 of them, 4 of them, 5 of them, and I could keep going, but all the way up to 150. So that's actually 151 calculations, even by using the complementary event idea. Still a lot of calculations to do. Oh, by the way, it does work out to be 0.9996. But obviously that's not the most efficient way of doing it. If I was to draw up the polygon of those results, we'd end up with something like this. And what we just found was the area to the right of 150. So all the values greater than 150. Something interesting about this graph, it has a mode somewhere in the middle of the range of values. It is symmetrical when we look at it. And the frequency density tails off pretty rapidly as we move away from the modal class. Well, they were all the features of a normal distribution that we saw before. And so this is why we can approximate the binomial distribution with a normal distribution. It satisfies our requirements for a normal distribution. If we assume it is actually a normal distribution then, we're going to need to know the 2 pieces of information we like for a normal distribution, which is the mean and the variance. So let's work it out. We're saying, remember, it's binomially distributed, 1,200 in total, probability 0.16. The mean would be n times p for a binomial distribution. So we know the mean is 192. The variance, np, 1 minus p, that's 161.28. I'm going to propose we can approximate it with this normal distribution, with the average being 192 and the variance being 161.28. But now I'm going to standardize the data. So if I turn it into the standard normal distribution, where the mean is 0 and the variance is 1, via our transformation, z will be x minus the average over the deviation. Then probability that x is greater than 150, well again I'm going to use the complementary event idea. So that's the same as 1 minus the probability of x being less than or equal to 150. But standardize that now because we're assuming it's a normal distribution. So I end up with z being less than or equal to negative 3.31. Now I can look up my table of values and I end up with 0.9995. Remember our answer when it was binomial was 0.9996. So how different is that? Well, the percentage difference, there it is, 0.008%. So it's a pretty good approximation. So when is it okay to do this? When are we allowed to approximate the binomial distribution with a normal distribution? It's those 3 key features of a normal distribution that we're looking for. The mode needs to be somewhere in the middle of the values. It needs to be symmetric. And the frequency density must tail off pretty rapidly as we go away from the mode. So let's just have a look at some and see, would it be okay or wouldn't it be okay to do it? Here's one where the probability is 0.125 I've done this for different values of n. So the number of times we repeated the trial. If it was only 10 times, so this is the first blue curve that you see there. P works out to be 0.125, Q is 0.875, of course, for all of these. But NP, 1.25, NQ, 8.75. And I'm saying no good, because if you look at the left of that curve, it sort of just stops. It doesn't tail off. No good. The orange one there is when n equals 20. Still no good. The grey one, n equals 30. Nope, still doesn't tail off on the left. No good. The yellow one, when n equals 40. Well, I've put both a tick and a cross on that one because it's starting to tail off, but hasn't really done it yet. Whereas the next one, at 50, I'm happy with that because it is tailing off on the left. I think it's satisfying those three conditions. So I would say, yeah, okay, for n equals 50, I think it's all right to approximate. What about if the probability was 0.25? Again, asking those same questions, let's have a look at it. The very first one, when n equals 10, nope, it just stops. It doesn't tail off. 20, however, it's starting to tail. Again, I've said, oh, maybe you could, maybe you couldn't. It's sort of on the borderline there. But once we get to n equals 30 for this one, I think, yeah, I think it is tailing off. And then obviously 40 will and 50 will as well. Okay, let's increase the probability to 0.375. Well, n equals 10, still no good. 20, yeah, I think it's okay. I mean, we can see that it's started to go asymptotic there to the x-axis. And then consequently 30, 40 and 50 are all okay as well. 0.5 and 10 now, it's starting to begin to look okay. It's in that borderline territory, but all the others are fine. What sort of rule can we come up with this? Have a look at what NP is and also NQ. Once it starts getting above 5 for both of those, it tends that the curve seems to be all right. So there's a rule of thumb we can use. If NP and NQ are both above 5, then I'm happy to use a normal approximation for the binomial distribution. Now, what we're doing, remember, is approximating the area under the polygon. I've got ones that are 1 unit apart. And remember, when you draw up a frequency histogram, you'd start a half in front or a half below. It might be more obvious if you think of the histogram. The area of the polygon is actually not going from a to b for the integral. It's a minus 0.5 and b plus 0.5. And so sometimes you hear people talk about this continuity correction, and that's for small amounts. So instead of finding between a and b, they'll find between a minus 0.5 and b plus 0.5. But as I say, it's for small samples because it tails off very, very quickly. Once you've got large numbers, at those extremities, well, it doesn't really matter. 0.5 is going to be insignificant. So you don't really have to worry about it. In fact, I wouldn't be worrying about continuity correction at all unless they specifically ask you to deal with it in the question. I think it's going to be unlikely that they will. But if they do, then all right. Instead of finding in between A and B, we'll find in between A minus 0.5 and B plus 0.5. Let's have a look at the question I actually asked last year. So the first HSC of this new course. When a coin, and it's a biased coin, so there's not an even chance of tossing a head and a tail, the probability of attaining the head is 3/5. And we're tossing the coin 100 times. And we're told to let X be the random variable representing the number of heads. They've also told us, in case we didn't realise, that it has a binomial distribution. Either we get a head or we don't get a head. Find the expected value. Well, it's a binomial distribution. They even told us that. So the expected value would be n times p. So for ours, it'll end up being 60. We would expect to get 60 heads. By finding the variance, show that our standard distribution turns out to be around 5. Well, variance, NP 1 minus P, we get 24. Well, that standard deviation is the square root of the variance, 4.89. Yes, I mean, that's approximately 5 to the nearest whole number. They then tell us to use a normal approximation. So we don't need to decide whether we can or we can't. They're telling us we can. So use a normal approximation. Find the probability that x is in between 55 and 65 heads. So remember, it was a binomial distribution. We were repeating it 100 times. Probability of a head was 3/5 or 0.6. But we're going to approximate it with a normal distribution, and we've now found that the average would be 60 and the variance would be 24. We'll standardize it, so we've got our typical average of 0, variance of 1. Between 55 and 65 becomes that Z will be in between, and it actually works out really nicely. They made the numbers nice, but in between -1 and 1. Now, that meant, because it was exactly one deviation, we didn't have to do any calculations, because we know that 68% of the data would be in between one deviation above and one deviation below the mean. And that information's even on the reference sheet, so you could have just looked that up and got 0.68. Okay, here we go at 17C, where we're now going to use a normal approximation to our binomial distribution.